Okay, but now let me introduce the second speaker today is Nikolai Filonov, and I guess we will be talking about why $1 million problem is really worth $1 million, right?
Something like this, yeah. First of all, I would like to thank the organizers for organizing. It's a very interesting workshop, and for me it's the chance to visit Cambridge. Cambridge is wonderful, so thank you for it too, Leonard, Frederick, and so on.
And the weather today is much nicer than yesterday.
Yeah, thank you. Now let us consider the following system of differential equations. Un dot plus lambda to power 2n un minus lambda to power beta n un minus 1 square plus lambda to power beta n plus 1 un plus 1 equal to 0 on the interval 0 to t. We have also initial data un of 0 equal to an, some numbers, and here is a natural number 1, 2, 3, and so on. In the first line you have u naught, which is supposed to be identically 0, and there are two parameters, lambda which is greater than 1 and beta is some positive number. And probably now each of you thinks that why we need to consider this awful system of infinitely many differential equations, neither spectral nor ergodic, nothing is periodic here, why we need to consider it. There are two reasons. The first reason is that it is not my regular talk. I will do the regular talk next week, and it will be about spectral property of periodic operator. Everything will be as it must be. But Leonie and Frederick asked me to tell about this topic, so I will tell you. The second reason is that to consider this system is that this system is similar to Navier-Stokes equations in hydrodynamics, and so I will recall you this Navier-Stokes systems. dTu. So in order to justify why I write down one awful system, I will write another awful system of differential equations. dTu minus Laplace u plus u gradient u plus gradient p equal to 0. Here we have not only time variable but also space variable. Assumes that domain in space is, for simplicity, a torus. Then we have no boundary conditions and so on. We have also divergence-free conditions. Divergence u must be 0, and of course initial data u when t equal to 0 is a given function a of x. And well, here u is velocity of the liquid in a point x, p is a scalar function, it is pressure. Well, it's too much unknown function, so let me rewrite it this thing as, instead of it I can write p of u gradient u. It's a projector on the divergence-free subspace.
So p is different from p.
Yeah, but I can do nothing. This p is for the pressure and this p is for the projector. So it's
P capital.
Yeah, but it is p capital. Yeah. It's
very important.
well, if u is divergence free, then dtu is also divergence free automatically, Laplace u also, but this nonlinear term can be not divergence free, and so we can we can represent it as a sum of gradient of scalar function, which is pressure, and of something which is divergence free, and so instead of it I will write this projector, Leray projector or Wild projector or Helmholtz projector is known under different names. But well, the question is why these systems are similar. The reason is that both systems can be written in the abstract way, in the abstract setting, simply like that: u dot plus a u plus b u equal to 0 on the interval 0t, and u of naught is equal to a. And this equation, it's equation in a some Hilbert space. U it's a known function which takes value in a Hilbert space H. For this case, Hilbert space is little L2 of sequences. I forgot to say that initial data AN belong to L2. It's always assumed, and here the Hilbert space is H is capital L2 on the torus. Well, it's the space of such functions from L2 which satisfies a divergence free condition. But it's Hilbert space, and okay. Then A is a self-adjoint non-negative operator, unbounded. Everyone likes self-adjoint unbounded operators, non-negative. Moreover, here it's a linear part. It's simply a multiplication of your sequence of each component by lambda to power 2n. Clearly, this operator is self-adjoint and non-negative. And here, a linear part is the Laplace operator. And also, everybody knows that it is self-adjoint, non-negative, and unbounded. And what about nonlinear term? Nonlinear term supposed to be bilinear map. B is map from H times H to H. It's not a bilinear form, it's a bilinear map. It takes two vector from your Hilbert space H and gives you not number but the third vector. And this bilinear map B satisfies two important conditions. The first important condition is that it's the cancellation property. You take the scalar product of BUU times you take third times the same vector u, and this scalar product must be 0, well, for good enough u. Let's say for a dense set in your Hilbert space of u which are good enough. For Navier-Stokes, it's simple calculations. We need to calculate the integral over torus uj dj uk times uk dx. I mean the summation of the repeating indices, and it's we can write dj uk as 1/2 dj of modulo u square, and so we can integrate by parts. It's minus 1/2 integral over torus dj uj u square dx. And so it's 0 due to divergence free condition. And if u is good enough, if we can take the derivative, calculate the integrals, then it's 0. And the same thing is fulfilled here. We can calculate sum over n from 1 to infinity of this nonlinear term times un minus lambda to power beta n un minus 1 square un plus lambda to power beta n plus 1 un square un plus 1. And clearly it is 0 because this series is the same series. The second series is the same as the first one, shifted n to n plus 1. And so it's 0 if all series converge, then it is 0. And it's a reason why we choose the nonlinear term in such a way. We cannot take only one term, because then we cannot have the cancellation property. But if we can these two terms, then it satisfies the cancellation property. So, well, it's okay for this condition. And the last condition for this map B, it's also unbounded map, but it must be bounded by something. So we assume that B of UU, the norm of this thing, must be estimated by some powers of the operator A to power sigma 1 u times A to power sigma 2 u. Something like that. Well, for the Navier-Stokes equation, A is a Laplace operator, and so the smoothness of functions is the same thing when one says that u belongs to domain of the sum power of the operator A. Is the same thing that to say that u belongs to some Sobolev space. Well, so we need we have such an estimate. Here the orders sigma 1 and sigma 2 can vary, but the sum is fixed. And for this system, it can be calculated immediately. What we need something like that. Lambda to power beta n un square must be estimated by lambda to power 2n sigma 1. It's our operator A to power sigma 1 times lambda 2n sigma 2 un. And so sigma 1 plus sigma 2 must be beta over 2.
So you're saying that the relation between those two problems, discrete and continuous Navier-Stokes, is that they obey similar conditions, right?
Yeah. I list here the main first features of the Navier-Stokes system. It's not all, but they are.
Is it also, could I interpret it also in the way that if you do periodic Navier-Stokes and try like decomposing everything in a Fourier series and writing system for Fourier coefficients,
it will be something like that.
More complicated version, but in some sense somewhat resembling this one, right?
Yeah, it will be something like that, but you will have for nonlinear term the infinite time each un will interact with all other un, and so we simplify it by taking only two terms. Yeah, it's one of the ways to derive this system. Yeah, and well, I have to calculate this. To show this inequality for Navier-Stokes equation. It's simple by
Because in the case if you do this, right, take a periodic Navier-Stokes, then the unbounded A will not have its eigenvalues growing exponentially, right?
Yeah, you're right.
I mean, the spacing is going to be different. And,
The spectral property of A's are slightly different, but it doesn't matter really for
really
this.
because, okay.
Well, so I have to calculate this. What is this inequality for Navier-Stokes equation for this term? I have to estimate the integral over torus of u gradient u square dx. It can be estimated, for example, by integral of u to power 4 square root of it times the same thing for the integral for the gradient of u to power 4 integral and square root of it. And then we use the embedding theorems. In order to have this integral finite, we need to use the space W d over 4. It's the space which is embedded in L4. And here clearly W d plus 4 over 4 is embedded into W14. And so we have to take the in this inequality we have to take a Laplace operator in the power so sigma 1 must be equal to d over 8 and sigma 2 d plus 4 over 8, and so sigma 1 plus sigma 2 is equal to d plus 2 over 4. Okay? And it's the answer for the question where in this model problem where we have the dimension of the space variable. Yeah, for the Navier-Stokes equation, it's well known that situation in two-dimensional and situation in three-dimensional cases are very different. But in the left on the left blackboard we have no x, we have no space variable, but this dimension is hidden in these estimates in this inequality, and so the correspondence is that beta is d plus 2 over 4. So the most interesting case in this problem is beta equal to 5/2. Now what I mean when I said that these two systems are similar, I mean that we consider this system, which is more simple than Navier-Stokes equations. We consider this system as a toy model for Navier-Stokes. If you prove something for this system, it gives you nothing for the Navier-Stokes. If you prove some theorem, it gives you nothing. If you construct some counterexample, it gives you nothing. But it can give some intuition, what here we have to wait. The Navier-Stokes equation, it's too complicated. You cannot keep it in mind when, say, you go in the underground. And if you cannot keep in mind the problem when you go in the underground, then you cannot solve it. And I think that it's the reason why the Navier-Stokes equation is not solved till now.
Even Navier-Stokes, but periodic Navier-Stokes. Will it be worth $1 million or not?
Periodic Navier-Stokes 3D, yeah, $1 million.
Periodic.
exactly periodic. Well, there are two options: either the whole space, either periodic. Case.
$1 million.
Well, what about $1 million? It's not to me. It's not.
Forgetting about dollars, it's about the same level of difficulty, right? Periodic or not, right? For analysts.
When the problem are not solved, nobody can say about the difficulties. Well, so now we concentrate on this problem, and let me first define the types of solutions. The first definition is definition of weak solution. By weak solution to this problem, I will call any sequences UN of T such that they are smooth in T. All functions must be C infinity in T. And the system is fulfilled. One and one is must be fulfilled, and then it's a weak solution. When I will speak about a smooth solution or good solution, here the goodness of solution, it's this story about in what domain of which power of A your solution does belong. And so here the smoothness or goodness of solution is the velocity of the converges UN to 0 when n goes to 0. This velocity is the goodness of solution. Well, so for weak solution, I assume nothing about that. And the next important notion is the Leray-Hopf solution. So definition 2, we call the sequence UN of T Leray-Hopf solution if it's a solution of our system, and if we have also the following estimate: 1/2 sum of UN of T square plus integral from 0 to T of sum lambda to power 2n UN square. This sum must be less or equal to 1/2 sum of an square. It's something like conservation of energy. Well, not conservation, but non-increasing of energy. And it's not difficult to show that for any initial data from L2, you have at least one Leray-Hopf solution. It's a common thing. Well, it's not the proof, but briefly, you take not all this infinite system, but you take it till some number n capital. You put UN plus 1 to be 0, and then you have ordinary differential equation which takes value in some Euclidean space. You have a global in time unique solution, And then you take different n capital, and you can choose a subsequence of solution which converge to something, and this something will be a solution of your initial problem. And for each particular solution of this finite system, you have here the exact equality, but when you take the limit, you can have only the inequality. So, so the Leray-Hopf solution always exists. Yeah.
The existence of the global solution, even for one-dimensional equation, is it obvious? It's non-linear.
It's not a good question. For a finite dimensional equation, you have a solution on a small interval of time. Okay? And this small interval of time depends on your initial data, on namely on its L2 norm. But due to this cancellation property, this one, you have this equality or inequality doesn't matter, and so your L2 norm of your solution will be always bounded by the same thing at all times, and so you have then solution on the next small interval, and the length of this small interval depends only on this thing, and so it's constant, and so you have global solution. It's the reason why this cancellation property is very important here. Well, next I have to give the definition of a strong solution, but I will do not do it. I will give the formal definition of strong solution, and warning the sense of this word strong solution will be different in different cases. But it means something like that UN tends to 0 when n goes to infinity fast enough. Well, now what is known about?
But is there some reasonable analogy, because all these weeks strong solutions of this thing and Navier-Stokes?
Yeah. These definitions are borrowed from the Navier-Stokes theory, and you have many theorems from Navier-Stokes theory here by the same. For example, you have the existence of strong solution on small times also, and you have the uniqueness of strong solution amongst Leray-Hopf solution, and so on. But also you have the existence of strong solution. What is known? Theorem 1 is due to Cheskidov in 2008. He proved the following theorem. If beta is less or equal to 2, and if initial data are good enough, say lambda to power to n 8n square, this sum is finite, then there exists a unique strong solution, and everything is good. Strong in the sense that the same sum and even the supremum over time of it is always finite. But it is also for beta less or equal to 2. And in the same paper, Cheskidov prove the following result about a blow up. If beta is greater than 3, and if all initial data are non-negative, then even for very good initial data, the solution cannot be strong in the sense that the integral over time of some lambda to some power 2 beta over 3 plus epsilon n un of t square, and everything is to power 3 half, will be infinite. The only condition that some norm of initial data must be big enough. You can even take all a n be 0 beginning from n equal to 2 if a1 is large enough. Then this for any solution you have something which is infinite, and so you have blow up, and so there are no strong solution, and it's for the case beta greater than 3. So
this is for each capital T, or
yeah, well, this assumption that norm of initial data must be big enough depends on T. Yeah.
and beta greater 3, if we translate it to Navier-Stokes, it means dimension is 5 or what? Or
It means a dimension is slightly greater than 4.
okay, so 5.
Yeah. And beta equal to 2 means 2-dimensional Navier-Stokes, where everybody knows that everything is good. And so, yeah, you are right. The most interesting case is 5 hull, which is not covered by this result. And there is the next theorem, theorem 3, which is due some Italian mathematicians, Barbata, Marandin, Romito, who proved in 2011 that if we consider beta from 2 to 5 half exactly, and if we assume that lambda equal to 2, and that all initial data an are non-negative, then there exists a strong solution. Then you can guarantee that there exists a solution un strong in the following sense: un of t is O capital of lambda to powers minus gamma n for all positive gamma and for all positive t. And for initial data, they are supposed that they are non-negative, and no assumptions on smoothness, only that an belong to L2. And so from for the time 0, your sequence is only from L2. It's not good, but for any positive t, its solution is very small. And if you take the initial data a little better, then you can write here something uniform in t. Well, but it's a very good and interesting result, but naturally one could like to remove these two conditions, that all initial data are non-negative, and the second, the fixation of the value lambda also seems to be, it seems that this condition must be removed. And when I started to study this topic, I was absolutely sure that it's doable. And to understand what's passed here, either to prove the existence of a strong solution or construct a counterexample. And
Sorry, Kolya, all these results are about existence, right? What about uniqueness? What is known about it?
about uniqueness, it's known that if there exists a strong solution, then it's unique amongst a Leray-Hopf solution. It's also a general fact. It's not difficult. And so these all theorems that there exists a strong solution, and so you are fine. And well, and till now I think also that it is doable, but for the moment I'm unable to do it. And instead of prove or disprove the existence of a strong solution, I prove the uniqueness of Leray-Hopf solution. It's other question, but it's also interesting. So the main result now is the following one. I assume that initial data are good enough. It's for any range of parameters lambda and beta. Assume that initial data are good enough, namely an is little o of lambda to powers 2 minus beta n when n goes to infinity, and then I can say that there exists, it's well known, a Leray-Hopf solution, and it is unique. So for good enough initial data, I can prove the uniqueness of the Leray-Hopf solution, and I have to repeat that. Well, it's
greater than 2.
sorry.
Beta greater than 2 probably.
Well, for this, you're right. If beta less or equal to 2, this restriction is not a restriction, because an belongs to L2, and so it's always fulfilled. But due to Cheskidov, for beta less or equal to 2, everything is wonderful. It was already wonderful before me. And for beta greater than 2, it's some restriction of goodness of initial data, but then in such case, the Leray-Hopf solution is unique. And I know that there exists a unique Leray-Hopf solution, but now I don't know if it is strong in some sense or not. And for beta equal 5/2, and for beta greater than 3, we know that it can be not strong due to Cheskidov.
What about uniqueness of weak solution? Is it known that it doesn't hold, or I mean, what?
Wait a moment.
Okay.
And now the last point, it's the story about a steady solution, about stationary solution. We consider this system of differential equations, but well, it's too complicated to keep in mind when you go in the underground, and so you can remove this term with derivative, and so I call the stationary solution the sequence an. It's a number sequence. There are no functions more. It's a number sequence which satisfies these equations: lambda to power 2n, an minus lambda to power beta n, an minus 1 square, plus lambda to power beta n plus 1, an plus 1 is 0. What about the non-trivial stationary solutions? Well, you can consider this equation as a recurrent formula for finding an plus 1 via a n and a n minus 1. And so everything is determined by two first terms, a1 and a2. And moreover, if you consider this, well, I forgot to say that a0 must be 0. And if you consider this equation for n equal to 1 for the first equation, then you have now this term, and so you can find a2. So a2 is fixed, and everything is regulated by the first number a1. You have some a1, then you have the whole sequence, which with different behavior on the at infinity. And the question is, what about this behavior at infinity? And the answer is the following. So it's the next theorem. The answer depends on beta, and critical case here is beta equal to 3. I will not say what is true for beta equal to 3 and for beta greater than 3. I know the truth, but well, for simplicity, let us assume that beta lesser than 3. It's the main interesting case, and then I can guarantee that there exists non-trivial stationary solution an such that an is O capital of lambda to power 2 minus beta n when n goes to infinity. There exists at least one sequence with such behavior, and this cannot be improved in the sense that for any non-stationary solution to this equation, we can guarantee that lim sup of an times lambda to power beta minus 2n is positive. For any stationary non-trivial solution, we have this estimate, and there exists at least one sequence which have exactly this behavior. Well, this means that if beta lesser or equal than 2, that there are no stationary solution in L2. But for beta greater than 2, you have such solution, and the important point that the stationary solution cannot be Leray-Hopf solution. In the definition of Leray-Hopf solution, where it is, we have this inequality, and so if you have stationary solution, then this sum is equal to this, and this integral is positive. So the stationary solution cannot be a Leray-Hopf solution, and it means that in this case you have non-uniqueness for weak solutions, because you have a stationary solution, it's here, and you have always the Leray-Hopf solution, and they are different. So the picture now.
Do you know how many stationary solutions?
I don't know.
So in principle, there could be more than one.
Yeah. Well, it could be more than one, and even it's a good question, because I forgot to say that the part of this theorem was done in the same paper of Barbata, Marandin, and Romita. They prove this thing for the case when lambda 2 powers 2 beta minus 6 less than 1 over 3. And in their case, the stationary solution is not unique. Yeah. But if you fixed initial data, then you can prove that you have two weak solutions, the stationary one and the Leray-Hopf solution. And so the picture is as follows. Here I write the condition for initial data, either O capital of lambda 2 powers 2 minus b n either little o of the same thing. And here I write what kind of solutions we consider. Either weak solution, either Leray-Hopf solution. And so here we have that it is not unique. I don't know what I have to write here, and here we have the uniqueness. And so, well, I cannot say that this result about the uniqueness of the Leray-Hopf solution for good initial data is sharp, because I don't know what's happened here and here, but it's sharp enough in the sense that if you take initial data a little bit worse than this condition, and if you consider instead of Leray-Hopf solution the notion of weak solution, then you have non-uniqueness. Well, that's all. Thank you very much.
Thank you. Any other questions?
I have maybe a remark, because several years ago I also worked in this nonlinear Navier-Stokes stuff. I guess the problem there is that, indeed, as Kolya said, nobody knows what to do with real Navier-Stokes equation. That's why people create different model problems. But I would say the bad thing about these model problems is that depending on whether people believe in where we have global solution for Navier-Stokes or we have a blow up for Navier-Stokes, they create slightly different discrete toy models which satisfy more or less the same nonlinearity and these cancellation properties, but depending on what they put there as coefficients and as other things, they obtain either global solution or blow up. I guess the principal difference between these toy models and the real Navier-Stokes, that in spite of existence of cancellation law, there is no divergence-free condition in discrete models. And this is a big deal, because if you consider Navier-Stokes equation, remove pressure and divergence-free condition, then everything is absolutely clear. Even for fractional Laplacian, for which power of Laplacian you have global solution, for which power of Laplacian.
No, Roman, you broke the cancellation property. If you remove pressure and divergence-free condition, you broke the cancellation property, and it's
right. In this case, you break the cancellation property, but you can add additional restriction as a global L2 bound or something like that, and that's what kind of happening when you consider toy models. So because
we want cancellation property. I will not give up cancellation property.
No. Well, in the toy model you have cancellation property, but you lose divergence, and so it makes the difference. So I don't say it is equivalent when you remove all this pressure and divergence-free condition in Navier-Stokes, but I just want to say that absence of divergence condition for toy model is the biggest difference in fact. Because I guess you said it to me about recent Tau result that it is not possible to prove something about Navier-Stokes using standard properties which people use there. So, and of course, real differential equation can have more hidden symmetries which can kind of increase critical power for existence.
That's why they pay $1 million for this, yes.
Yeah.
And will not pay Kolya even if he proves.
I'm afraid they will not pay Kolya even if he proves, because in this case they can say that, well, he proved something not exactly the same, but
but I do not pretend.
So, coming back to these stationary solutions, are there at least not more than finitely many of them? Not more than countably many? Would we guarantee it?
It depends on the these parameters lambda and beta. In some situations, there are continuously many stationary solutions.
Ah, okay.
You have an interval of A1 such that you have this behavior.
Any further questions?
Then what is the method of proof of the results?
It's not a little question. The method of proof is that in this story, the case when you have something non-negative is most important. Firstly, you can prove, and honestly, it was done for if you have all initial data non-negative, then even the weak solution is unique. It was done not for this model, but for the model without this term. So the model for not for Navier-Stokes, but for Euler equations. And this result can be repeated here. And the next idea is that you can take the case where not all numbers an are non-negative, but an non-negative for beginning from some place. And then you have this uniqueness. And then you, and the next observation in that if you have for some times the UN of t which have known this property, so you have UN of t, you have a sequence nk such that UN of k of t is lesser than 0. Yeah, you have only two possibilities. Either the sequence is such that all terms are non-negative beginning from some place. Either you have a subsequence of UNKs which are negative. And if you have such situation at some time t, then here the solution must be strong. It can be proved. And then you consider your Leray-Hopf solution, and you consider the first time t star is infimum of such t where this sequence UN of t does not satisfy this property, say doesn't belong L2 plus, where L2 plus is the set of such sequences. And then before this time your solution is strong, after that time it's unique, and you have to do something in the neighborhood of this time, and then you are done. I'm afraid I cannot go to further details.
Other questions? Okay, let us thank both speakers today.